and Gerhard and the Franklin Institute, thank you very much for this wonderful conference that you've got here. Okay, I'm going to change gear a little bit from the previous speaker, and I'll probably contradict one or two things he says, but let's see what's going on. And for the record, please remember, please delete your image of me as a Bohmian. For this talk, I am not a Bohmian, okay? And I want to report some work that some ideas that came to me and looking accidentally at certain papers. And a whole load came together in about 5 or 10 minutes, which was very interesting and very exciting and different from what I've done before, but not different from what I've done before. Okay, and I want to thank Maurice de Gosson, Rob Flack, and Bob Callaghan for their help in this work, and particularly for Maurice, who taught me everything I know about symplectic algebras, but I'm not sure whether that's a compliment or an insult, actually. Okay, so what happened? Came across some surprising results. The first one was that I was playing around with von Neumann's 1931 paper that was after the book, and it was totally different from his book. He didn't have Hilbert space in there as such. And it turned out that it was identical to Moyal's approach, which I'd studied very earlier on, and I'd been presented it was a classical approach. But in fact, I found the mathematics was identical to von Neumann. And this is the von Neumann which gave rise to von Neumann algebras. Then when I was looking at von Neumann, I found that, at Moyal, found that he was treating quantum mechanics as a statistical theory, as a generalization of classical statistics, and he worked out the conditional expectation values for the momentum and energy, and it turns out that they are related to the zero mu components of the standard energy momentum tensor of quantum field theory, which I didn't know. Then when I was looking further in the appendix at Moyal, I found that his momentum was, in fact, the Bohm momentum, identical. And this also holds for Pauli and Dirac. Moyal didn't have that, but we showed that later on. Then what we find there is that the Bohm-Moyal approach is really about non-commutative probability theory. And I'll explain that. And then the really big surprise was that I found that the Moyal-Bohm momentum was actually a weak value of the momentum operator. And this I found very surprising. And the only way I found that out was people kept coming to me and saying, what is this weak value? What are these things? What is Aronoff and Weidmann talking about? And I and then I thought, well, perhaps as I'm supposed to know something about quantum theory, I ought to know what they were doing. And I found this result. And then you can measure these results, and then you can also show the Bohm momentum, the Bohm energy, the Bohm kinetic energy, are all weak values. If you can measure those weak values, then you can measure the quantum potential, so it no longer becomes something that a lot of people don't like for reasons that I don't understand. And then finally, and this is perhaps a bit controversial I want to turn your ideas on their head for a minute, but I think and that is, I want to say that classical physics emerges from quantum physics. Okay, I'm not but we'll just see why I'm saying that at this stage, okay? All right, so where did von Neumann start? Well, von Neumann started with a translation in X space and also a translation in P space. And he put them together into that object S. Let's see if that object S there. And that's just an element of the Heisenberg group. And of course, I grew up being taught that once you've got the Heisenberg group, once you've got the Heisenberg algebra, you've got quantum mechanics. It's not true. Because the people who use the Heisenberg group the most are people who are studying radar. So you're actually worrying about plane speed and how far away they are, et cetera, and you use the Heisenberg group to do that. So it's not simply quantum mechanical. Now, what I want you guys to pay attention to are these two parameters, alpha and beta. Not the operators, forget operators. Think about the alpha and beta. It turns out that they span a symplectic space. And you can handle that by means of a symplectic Clifford algebra, and there's something that doesn't work with conversion from my things to PowerPoint. It's equivalent to the enveloping algebra of the Heisenberg algebra. And in the symplectic group, and Morris, are you going to talk about the metaplectic group? Yeah, okay. And that metaplectic group comes out as a as a covering group, but it's already in the algebra. You don't have to do anything exciting for it. It's there already. Okay. So what von Neumann showed was that there's an isomorphism between the operators and these functions on this symplectic space. So you can do all of quantum mechanics on this symplectic space. And the way you do that is this connection between the, oh, sorry. Wow. Sorry, I'm a very bad driver. And you can do it through this connection here between the operator and this object here. And this is called a symbol for some reason or other. That's what happens when you let mathematicians get hold of it. And then what you find is, in order to get expectation values to see whether you've got the agreement with experiment, you formally introduce, I'm going to call it a density element. It's, for physicists, just think of it as a density matrix. But it's a density matrix which you were talking about. And it's done in terms of elements of the left ideal and elements of the right ideal. So you can combine these two to generate the density operator, or the density matrix in this case. And then what Moyal did was to say, oh, look, why don't we treat that as a probability distribution, and then we treat these as functions in this symplectic space, and we can get expectation values just as you do in ordinary statistics. But of course, we know the problem was that this probability measure takes on negative values. And when I first saw that many, many years ago, I thought I just threw Moyal's paper out of the window and said, I don't want to know anything about it. I wish I hadn't have done that now. But in fact, the reason why you're getting it is because you're essentially dealing with a non-commuting probability. And therefore, you've got a non-commutative symplectic manifold, which is the basic manifold in which this takes place. Okay. Now then, looks like a nice function, but unfortunately, if you look at it, how does it multiply together? And you find that it doesn't multiply commutatively. It's a non-commutative multiplication. And that is the Moyal product, the star product there. But please note, this is the correct result, but it was already in von Neumann in 1931. And Moyal, I hope, re-derived it in his paper in 1949. Okay, and to see what it means is if you put just alpha, beta, and you do that star multiplication there, well, apart from the H bar, it's just the Heisenberg relation. Okay, so what you've got there, then Moyal said, let's have it as a non-commutative symplectic space. Okay, if you've got a non-commutative product, it's best to take two brackets. One is, oh, I keep doing it. Sorry. One is the Moyal, the commutator, if you like to put it. And the other one is the Baker bracket. If you're a mathematician, it's a Jordan product, or the anti-commutator if you're a physicist. But we're not in the quantum mechanics yet. Just wanted to use those words so that you're prepared for what I'm going to say. Okay, now what Moyal showed, and this is quite a feat, was that the product is actually this two-way differential operator here. That operates on that function, that one on that one. You operate that one, sorry, I'm shaking like mad. That one on that one, and you take them away. And you can see there's a kind of Poisson bracket in there. And in fact, when you go to, and here they are, sine and cosine. And when you go to the classical limit, order h bar squared, you find that the Moyal bracket becomes the Poisson bracket, and the Baker bracket becomes the ordinary commutative product. So you have classical physics sitting in this as an approximation. And that was my thing about emerging classical physics emerging from quantum mechanics. That's the whole reason I put it in there. Okay. Now then, we want dynamics. And when we've got a non-commutative dynamics, we've got a problem, because if think about a Hamiltonian operator, if it's non-commutative, you can either operate from the left or you can operate from the right. So what I suggested was, sorry folks. What I suggested was that we put in on the top here, when we were operating from the left, the arrow goes left, and when we're operating from the right, the arrow goes right. And now what I do is say, okay, let's add these two equations together. And when I add them together, I subtract them first of all, and that minus sign becomes a plus, so I get a derivative there. And what is this? This is nothing more or less than the classical Liouville equation. So this is the conservation of probability coming out of this. Then what about the Baker bracket? This was very interesting. What about the Baker bracket? Well, the real problem is it's not a derivation because of that wretched negative sign in there. And I went around asking people, what is this antiderivative? Nobody would give me any answers. So what I did was what I learned from David Bohm, and whenever you're in trouble, write the wave function as RE to the IS and see what happens. And we do, it still looks dreadful, doesn't it? But if you go to the limit of order h bar squared, what you find is that bracket actually, that equation actually just becomes the classical Hamilton-Jacobi equation. So you've actually got the classical Hamilton-Jacobi equation in this structure as well. And that was very kindly the direction to use the Baker bracket. I have to thank David Hiley of Durham University, who emailed me, because I said, is this a new equation? And he said, I think it's related to the Baker bracket. And this opened up, that comment opened up all this for me. Okay, so there we have. We've got a phase space. Oh, you can't do quantum mechanics in a phase space. Well, you can, actually, but I want to say more about it. And you've got these two basic. Okay, now I want another surprise. Surprise number 2. Working in the appendix of the Moyal algebra. And what do I find? I find Moyal defines something which he calls the Moyal Momentum. There it is. Oh, it looks horrible, doesn't it? What the hell does that mean? Okay, do the usual trick. Psi equals RE to the IS. And what you find is it's just grad S, which is just the Bohm momentum. Okay, so then what you do is say, all right, now what Moyal asked was, what's the equation which transport this momentum? It looks pretty good. He used Heisenberg's equation of momentum. It's a mess. This is a one line from 3 pages. And then if you, again, put psi equals RE to the IS so we can see what's happening, and you find that it's nothing more or less than what we called the quantum Hamilton-Jacobi equation with the quantum potential there. And this was done in 1949. This paper was published. And David Bohm's paper was 1952. So already the ideas were there in Moyal's work. Okay. So what we've got then, we can now, you see why I've got these gaps in here. I've now got the Bohm phase space, because there you define this momentum PB. And then you've got this equation, it corresponds to that. This equation corresponds to that. Lovely. But then all you guys who are quantum physicists who don't like what we do, but quantum mechanics only takes place in configuration space. Okay, so that's why I've got configuration space. Now, how do we fill that equation up, okay? Right, well, remember I'm dealing with the, this density operator, this density matrix, which is, for the purposes here, it's idempotent of rank 1. Any matrix of rank 1 can always be written in terms of wave functions. So the wave function is something which we don't start with in this theory. The wave function is something which is a derived concept or a limiting concept. And I put a heuristic argument on here, which I love, because I asked people, do people know what the standard ket is? And everybody said, of course we do. And I say, all right, how do you write it? and they go line, psi, bracket. No. There is no line on this. And this was actually Dirac's symbolic attempt to get a left ideal. And he's also got a standard bra, which is the right ideal, and it stops you multiplying from the left. This is why it's the right and left ideal. He put it in. But if you put the two together, it turns out that it's an idempotent. And it's what we want, because in order to define left and right ideals, you need an idempotent. And that's the key to the whole thing that I actually do with the geometrical algebra, is to find the idempotency. That's what you were finding, by the way. You've got idempotency. Yeah, good. Good, he agrees with me. That's great. Okay? And now what you do is, all right, now you've got to be careful, because this is a non-commutative object. You've got to multiply from left, and you've got to multiply from right. So you're back again. What do I do for the equations of motion? Well, I take the Schrödinger equation, and I take its conjugate. Now, normally we say the conjugate tells us nothing new, and throw it away. But if you keep it, then what you can do is you can form the difference, and there you get the the commutator, and you take the sum, and there you get the anticommutator. And your two examples, Prof, are examples in those two algebras. Okay, let's go on a bit further. So what we've got there is the Liouville equation, and what we've got here, and this was the new equation. This is that Brown, student of mine, Melvin Brown, lovely thesis he had, showed how that we got this result out. And I thought it was a new equation, but then I found that physicists don't know this equation, as far as I know. And if there's any physicist in the audience who knows it, I would love to know why or how he knows it. But the chemists know it. Okay? And it's absolutely essential. This is, I think I had is he here? Is Andrei Krennikov in the audience? No, he knows my talk, so he's gone away. He was trying to build everything out of this equation here, and you can't. You need this equation, otherwise you don't get the full quantum mechanics out. And that's what the chemists know, because they work out energy levels using this particular process. Okay, how am I going? All right, so now what we've got then, we can fill in this configuration space. Am I doing all right? Okay. I've got these two equations. Look, that one corresponds to that. This one corresponds. But what I haven't shown yet is how you go from here to here in this structure. All right? So very easy. Project the operator. Now, these equations are operator equations. Now project these operators into some representation. And I take a general representation for the moment, but what we're really interested in is project it into the X representation. Then we've got configuration in X space. And what we find is this equation with the commutator in gives me the conservation of probability. And this one, I've chosen the harmonic oscillator because I want to do something in the next slide. It's symmetrical in X and P. It doesn't have to be a harmonic, it can be anything you like. But because of the symmetry, you'll see why I want to do it. And then what you find is you get the quantum potential coming out there, okay? Now then, but that's not the only representation, because you can also do the P representation. And Heisenberg criticized David Bohm right at the beginning by saying, it's all very well for Bohm, but he's not got the P representation in there. And here's the P representation. Notice that the P representation, you have to do everything in P space, and that's why I took the P squared, X squared. And what you find is you get a quantum potential in P space. And then you can work out trajectories. Notice, and this was a bit of a contention with some people who are Bohmian mechanics. I showed this to Shelley, and he did not like it, because his whole theory depends upon the guidance condition. And you can't call that a guidance condition. But what we've got here are two complementary phase spaces, and there's an interesting discussion that can go on with that, because the geometry is slightly different. So what I'm claiming is, this is why I say I'm not a Bohmian in the traditional sense, because Bohmian mechanics is only a fragment of this, Now I want surprise number 3 was the energy momentum tensor. What I did, and this was Bob Callaghan said to me, why don't you use the Lagrangian? I said, because it's okay. In the end, he pestered me so much, I did actually write it out. And what I found was that if you use the Schrodinger Lagrangian that gives you the Schrodinger equation, that's that one there, then you find this general result, which shows, if you compare that with the Bohm momentum or the Moyal momentum, you see that there's a relationship between the components of the energy momentum tensor, the local energy momentum tensor. So what we're doing here is local energy and local momentum. But in order to conserve it, we had to introduce the quantum potential. So if you think of quantum potential as a new quality of energy, then that gives you the conservation of energy, momentum energy. Now, what do they do in the standard theory? In the standard theory, what's gone wrong? Oh, sorry, I have to add one more point, which I forgot. If you want to do the Pauli and the Dirac equation, and remember that Bob and I have now done the Dirac equation in the Bohm interpretation completely. We've got quantum potentials, the whole lot, and it's a brilliant bit of work. Although I say it myself, it's a lovely bit of work and the only way I can get it is out of the orthogonal group, out of the orthogonal Clifford algebra. This is the algebra you were actually using. I recognized immediately what you were doing. Okay, and then what's the relation of this to the usual theory? The usual theory is we integrate over all space, and then we use our conservation of energy and momentum. So we're not using the usual theory, we're just looking at the components that lie underneath the usual theory. So Bohm's theory is not about hidden variables. He made it into one, but it's not necessarily, the formalism is not about hidden variables. Okay, now then, the weak values. As I say, what we have here is that there is a relation. What I found was a relation between the Bohm momentum and the weak value of the momentum operator. Therefore, if we can use the weak values, what is a weak value? Well, a weak value is simply you take this, which is the normal transition probability amplitude, and then you put this funny thing underneath. And if you do that for the Bohm momentum, you actually get the result coming out. And then what you find is, there's a slide missing, something's gone wrong. Oh yeah, now let me show you how you get this out, just in the last 5 minutes. You just simply write down the weak value. So this is the momentum, and you evaluate, you post-select it at x when you pre-select it at some time t. And then you just simply work it out. And what you find is that this expectation value is that, or that transition is that, divide by, and then use our little trick, of course, of always, when in doubt, write psi equals re to the is. Sorry to keep playing the record. But then what you find is that you get this expression. Now, the weak value is a complex value. And if you take the real part of it, it's just the Moyal Bohm momentum. But if you take the complex part of it, it's the osmotic momentum. And that's what Ed talks about, the osmotic momentum. So there's a kind of there's a possibility of the stochasticity lying underneath it. And then if you do this so you've got the real value, you take the imaginary part, you do that. Let's see, what else have we got to do? Oh, and then you can also go through and you can find the kinetic energy, and therefore you can measure the quantum potential. You could measure these, you could measure the quantum potential. When I discovered this weak value, I then found that Rick Levins had published a paper which confirmed everything I'd done. I felt good about that. But then also I found a paper by Howard, who's here somewhere, and he also had that expression. So that made me feel nice and comfortable. Okay. Oh, this is, have I got time? How am I going? Well. Okay. This is, what I'm doing here is I'm doing the Bohm approach for spin quickly. I didn't think I'd have time to put this in. Here we have the density in terms of the elements of the left and right ideal. I then know how to translate this information into those elements of the left and right ideal. And then I find the Bohm momentum can be written like this, Bohm energy can be written like that, and the Bohm kinetic energy is written like that. And then I forgot the Q on here, so this means that I can also do this for spin a half, but we can also do it for the Dirac equation. So we've got the complete picture. One thing that's missing is the many particle. Right, now let me get on, because otherwise Bob's going to panic, because Bob's following me. When I'd done this work, somebody came and showed me the Toronto experiment, and I did a somersault in the air as soon as I saw it. You can, because one of the criticisms that's always been made against us people who support Bohm is, why are you talking about the Bohm momentum, the Bohm energy, etc.? You can't observe the bloody thing, forget it. And now you can observe the thing. Oh, look at this. Now you can observe it. And in fact, look how close it was to the work that, that Chris Dewdney and Chris Philippides did way back in 1979, where we calculated from the guidance condition the trajectories. And now to see this thing here and say, wow, look at this, justified. Now the problem with this is that this is Maxwell's equations, and this is Schrödinger equation. And then if you talk about trajectories for Maxwell's equations, what are you talking about? Yeah? The thing you're talking about actually here is what you measure. Forget about the momentum. What you're measuring is Poynting's vector. And then you've got the question of what is the meaning of a Poynting vector for a single photon? Now, if you do Bates' experiment where it measures the angular momentum of the photon, you divide by the total number of photons in the beam, and you get a value for the spin, 1. Mechanically, you can do that. But here, well, David Bohm and I knew about this right at the beginning because there was a guy called Richard Prosser who also calculated some trajectories, and they were dreadful trajectories. And the reason for that is that he didn't have the computing power that you youngsters have now. And it looked nothing like that. But we were discussing this, and when we came to write our book, we said, well, how are we going to deal with the photon? Because you get into lots of trouble. You cannot have photon trajectories with the conclusion we reached. And in fact, that's why we went to field theory. And that's what we published in this. It's also in our book. We went to field theory and showed that bosons must be discussed in terms of quantum field theory. So when I saw Bob and he said he's interested in this kind of thing, I thought, okay, well, look, this is Schrödinger equation. These criticisms don't apply to the trajectories for the Schrödinger's equation. There's other objections that we know about. But then why don't we try and do experiments, new experiments, using atoms? And Bob is going to talk about that in the next lecture. Okay?
Thank you. Thank you. I guess we have time for quite a few questions. Yes, all few.
It's all very good. If you go further and you go into Moyal formalism and introduce also non-commutativity of momentum, you get an amazing sort of new phenomenon.
Yeah. Please, I'm a youngster in this game.
Yes.
So thank you for...
You can go and exercise a bit further.
Yeah.
Take this formalism and extend it to non-commutativity of the momentum itself. You have considered only configuration effect. You get the whole
Yeah, no. I wanted to say that these three theories, the standard quantum mechanics from the algebraic form, Bohm and Moyal, are the same thing.
Further generalize Moyal product, because Moyal product has been written in terms of the configuration.
Yeah.
Not go further than use momentum.
Yeah. Good, thanks.